Do you know that in space, no one can hear you scream? Or that dogs have super hearing powers? While dolphins can catch sounds that are way beyond our reach. Get ready to dive into the fascinating world of sound and explore how it travels, how different living beings perceive it, and so much more. In this chapter, Sound, we will explore the what is sound, including its production, propagation, and reflection. We will also examine the range of human hearing and delve into the applications of ultrasound technology. This video will be uncovering the fundamentals of sound and will mainly cover topics. What is sound? Production of sound and propagation of sound. Let us get started with our first topic. What is sound? Sound is a type of energy that we can hear. It is created when something vibrates or moves back and forth quickly. These vibrations cause the air around them to vibrate too, and these vibrations travel through the air to our ears, allowing us to hear the sound. For example, when you clap your hands, you are using your energy to make your hands move and hit each other. This action creates vibrations that spread through the air, and when these vibrations reach our ears, we hear the sound of clapping. Similarly, when a bird sings, it is using its energy to move its vocal cords. These vibrations create sound waves that travel through the air, and we can hear the bird's song when these sound waves reach our ears. In both these examples, energy is being used to create sound. This energy is transformed from one form, like mechanical energy, into another form, sound energy. This is in line with the conservation of energy principle, which states that energy cannot be created or destroyed, only changed from one form to another. Let us get it more clarified that how sounds are produced. Let's explore this by learning the next topic: production of sound. As already discussed, sound is produced when objects vibrate, which means they move back and forth quickly. Sound travels through different mediums such as air, water, and metal and reaches our ears. Let's take some examples from everyday life. Now, visualize yourself strumming a violin. When you draw the bow across the strings, they vibrate as well. These vibrations create sound waves in the air, which travel to your ears, allowing you to hear the beautiful music created by the violin. Think about the sound of a car engine. The moving parts inside the engine create vibrations that generate sound waves. These waves travel through the air, reach your ears, and you hear the familiar sound of the engine running. Now that we understand how sound is produced through the vibration of objects, let's explore why sound requires a medium to travel. To delve into this, let's move on to the next topic: the propagation of sound. In our discussion of sound propagation, we will explain. What is sound propagation? Sound is a longitudinal wave. Characteristics of sound wave and speed of sound waves in different media. So what is sound propagation? Sound propagation is the process through which vibrations from an object travel through a medium, such as air, a liquid, or a solid, to reach the listener's ears. To put it simply, when an object like a guitar string vibrates, it causes the particles around it to vibrate too. These vibrating particles then cause the neighboring particles to vibrate, creating a chain reaction. This chain reaction creates a series of high-pressure areas or compression and low-pressure areas or rarefaction. Suppose we have a tuning fork with two prongs, which is vibrating. When a vibrating prong moves forward, it pushes and compresses the air in front of it, creating a region of high pressure. This region is called a compression. This compression starts to move away from the vibrating object. When the vibrating prong moves backwards, it creates a region of low pressure called rarefaction. Sound propagates in the medium as a series of compressions and rarefactions, similar to how a slinky moves when you push and pull it. Moving forward, we will explore the nature of sound waves. Sound is a longitudinal wave. In these waves, particles in the medium, like air or water, move back and forth in a direction parallel to the direction of the wave propagation. The particles do not move from one place to another, but instead oscillate around their rest position. Imagine you are standing near a speaker playing music. When the speaker's diaphragm vibrates, it pushes the air molecules around it. The air molecules themselves do not travel from the speaker to your ear. Rather, they bump into the molecules next to them, transferring their energy. These air molecules oscillate back and forth as a series of compressions and rarefactions in the same direction as the wave propagates, and hence, it is a longitudinal wave. In contrast, there is another type of wave called a transverse wave. In transverse waves, particles oscillate up and down about their mean positions in a direction perpendicular to the direction of wave propagation. An example of a transverse wave is when you drop a pebble in a pond, creating ripples on the water surface. With the understanding that sound is a longitudinal wave, we will now study the characteristics of sound wave. A sound wave can be graphically represented to illustrate the changes in density and pressure as it travels through a medium. This representation consists of crests and troughs, which are the highest and lowest points of the wave, respectively. The crests correspond to compressions, which are regions of high pressure and density where particles are closely packed. On the other hand, troughs correspond to rarefactions, which are areas of low pressure and density where particles are more dispersed. These alternating high and low pressure regions create a wave-like pattern, with crests representing the peak of high pressure and troughs representing the lowest points of low pressure. The distance between consecutive compressions or rarefactions in a sound wave is known as the wavelength, denoted by the Greek letter lambda and measured in meters. In addition to wavelength, sound waves can also be characterized by their frequency, amplitude, and speed. The speed of the wave depends on the medium through which it travels. Let us study some of the important terms of sound and how they are correlated. Frequency, time period, and pitch are three terms that are interrelated when describing a sound wave. The frequency is the number of times an event, such as an oscillation of a sound wave, occurs in a unit of time, and it is measured in hertz. The time period is the time taken for one complete oscillation of a sound wave, measured in seconds. The pitch is how our brain interprets the frequency of a sound, with higher frequencies resulting in higher pitches. These three terms work together to describe the nature of a sound wave and how it is perceived by our ears and brain. Similarly, amplitude and loudness are two terms that describe the intensity of a sound wave. The amplitude is the maximum disturbance in a medium from its mean value during a sound wave. Loudness is the perception of the intensity of sound, which is related to the amplitude of the sound wave. Higher amplitude results in louder sound. These two terms help us understand how loud or soft a sound is, based on the strength of the sound wave. Now, what is quality or timbre? Quality, or timbre, is the characteristic of a sound that allows us to distinguish between different sounds with the same pitch and loudness. A sound with a rich quality, or timbre, is more pleasant to hear and can be described as having a warm or full tone. This term is important in understanding the aspects of different sounds and how they are perceived. Tone, note, and noise are three terms that describe different types of sounds based on their frequency content and our perception of them. A tone is a sound of a single frequency, which typically produces a simple, pure sound that is easy to identify. For example, in contrast, a note is a sound produced by a mixture of several frequencies that, when combined, create a pleasant or harmonious sound. This is often found in music, where notes are played together to form chords and melodies. On the other hand, noise refers to unpleasant and unwanted sounds that often lack a clear pitch or structure. Lastly, let's talk about the speed of sound in various mediums. Sound travels at a specific speed, which is slower than light. That's why we hear thunder after seeing lightning. The speed of sound depends on the material and temperature it moves through. It's slower in gases than solids and faster in higher temperatures. The speed of sound is different in various materials, and you don't need to know exact numbers. In conclusion, sound is a form of energy produced through vibrations that travel as longitudinal waves. The characteristics of sound waves, such as frequency, amplitude, and speed, affect how we perceive pitch, loudness, and quality. The speed of sound varies depending on the medium and temperature it travels through. In our next video, we will study the further details of chapter sound, focusing on sound reflection, human hearing range, and ultrasound technology applications. Hope this video has been useful in helping you understand the chapter sound. To enhance your learning experience and improve your academic performance, consider using EduRev app. You can find chapter overviews, captivating video lessons, and NCERT-focused quizzes for each chapter, all in one place.